An AC generator is a device that is used to convert mechanical energy to electrical energy. So let me just write this. This is a device that converts mechanical energy into electrical energy. We'll now take a look at the principle. If a coil is rotated in a magnetic field such that the angle between the coil and the magnetic field varies, then the flux through the coil is also a varying flux or a changing flux. Now this changing flux produces an EMF, and the EMF that is produced varies sinusoidally and is called an alternating EMF. So the name given to this device is an AC generator. Next, let us draw the AC generator. We'll just make a rough sketch. See, you have a coil. We have a coil like this. This coil rotates in a magnetic field. So you have a magnet placed over here. Say this is the north end of the magnet and this is the south end of a magnet. So you have a magnetic field from the north to the south direction. You have a magnetic field in this direction, and the coil is placed in this field. Now the ends of this coil over here, these are connected to slip rings. These are called slip rings. These are flat brass rings, and the ends of the coil are connected to these slip rings. And we have another slip ring which is connected to this end of the coil over here. And then you have carbon brushes. These carbon brushes, so at this end over here you have a carbon brush and you have another carbon brush over here. This is where we get an alternating EMF at these ends. So we have an alternating EMF over here, and you can also just quickly label the different parts. This was the coil which rotates in the magnetic field and is the armature, and then we have the permanent magnet which provides the strong magnetic field in which the coil is rotating. These are the two carbon brushes, this and this. These are the carbon brushes, and which are conductors and allow the current to flow out of the coil, and this over here are the two slip rings which are brass rings. Now we are going to find the magnitude of the induced EMF. Let us assume that the coil is rotated in a magnetic field with an angular speed omega. So the flux which is linked with the coil that has n turns in it is going to be phi, we know, is B dot A. B is the magnetic field and A is the area vector. So this becomes, if there are n turns, then this becomes n B A cos theta. Since this is the dot product of the two vectors, so we have cos theta over here. Now B and A are the magnitude, this B and A are the magnitude of the magnetic field and the area vector respectively. Theta is the angle between the magnetic field and the area vector. Now in place of theta we can put omega t, since omega is the angular speed and omega is equal to theta over t. Omega is measured in radians per second, so it is theta over t. So now for phi we can write phi as n b a cos omega t. Now we know that Faraday's law states that the induced EMF E is equal to minus d phi by dt. So we are using Faraday's law, and Faraday's law states that the induced EMF E is minus d phi by dt. Now differentiating this expression over here, we'll get the induced EMF as minus n. Since n is a constant, you can take it out of the differentiation. B and A are actually also constants because the magnetic field is constant and the area vector is not changing. What is changing is the angle between the area vector and the magnetic field. So differentiating cos omega t, we get omega sin omega t, and we also have a negative sign because the differentiation of cos x is you have negative sin x. So now differentiating cos omega t, we get omega sin omega t with a negative sign. So now the induced EMF becomes NB A omega sin omega t. Now this shows that the induced EMF varies sinusoidally, and we can just write this as the induced EMF can be written as E naught times sin omega t, where E naught, which is the peak value of E, is going to be N B A omega, and the value of sin omega t varies between +1 and -1. So the maximum value of the induced EMF is NB A omega, which is the peak value. Now if the rotation of the coil is expressed using the frequency of rotation, then we can replace omega with 2 pi nu. Say the frequency is nu, then we can replace this with 2 pi nu, and then we get N B A, and in place of omega we are putting this as 2 pi times nu. Now the EMF generated in the coil varies sinusoidally with time, as you can see from this expression over here, and it will produce a similarly varying sinusoidally current in any circuit that it is connected to. Now let's just take a look at the position at which the induced EMF is maximum as the coil rotates in the magnetic field. See, what I've done is I've just turned around this magnet and drawn it like this, just to make it easier for you to understand. Say this is the north end and this is the south end of the magnet. Now we have a magnetic field which is in this direction from north to south. So I'll just draw a few field lines. This is the magnetic field from north to south. Okay, we'll just put arrows to indicate the direction of the magnetic field. Now we place a coil in this field, and say the coil is placed like this. I've drawn this first position over here. If the coil is placed like this in the magnetic field, which is in the downward direction, in this case the flux linkage through the coil is maximum. The flux linkage phi is maximum, as you can see, because the number of field lines crossing the area is maximum. And if you look at the direction of the vectors, the direction of the B vector is in the downward direction, and the direction of the area vector can also be similarly taken as a as a vector like this, perpendicular to the area. So this 2 is in the downward direction. This means the angle theta between the area vector and the magnetic field is 0, and if this angle is 0, then cos 0 we know is 1. If you just look at the expression for phi, which is n b a cosine theta, so since theta is 0, flux phi is maximum. But now if you notice, as this coil rotates, say this coil rotates in this direction, in the anti-clockwise direction, as the coil rotates, for this position the change in flux, which is d phi by dt, d phi by dt is very small. So since the change in flux is small, the induced EMF is less, and at one position it is 0. Whereas when you have the coil placed so that the plane of the coil is along the field, if the coil is placed in this position, when the plane of the coil is along the field, or you can say the area vector of the coil is perpendicular to the magnetic field. In this case, theta is 90 degrees, flux phi is minimum, it is 0 actually. Flux phi is minimum, you can say that phi is 0, but d phi by dt is maximum, because as it enters from a region where the flux linkage is 0 to the flux, the change is maximum. So you get an output which looks like this, and the positions at which you have minimum flux, these are the positions when the plane of the coil or the armature is perpendicular to the magnetic field. When the plane of the armature is perpendicular to the magnetic field, at these positions you will get maximum flux but 0 induced EMF, and at positions over here, at these positions, which is something like this, when the armature rotates and the plane of the armature is parallel to the magnetic flux, you get maximum induced EMF.